before in the notes, hyperbolic PDEs. Okay, we saw last week that hyperbolic PDEs are perhaps the most common PDEs which are used in modelling, because they model things which move. Okay, something moves from one place to another. It's what we call propagation, and that's modelled using hyperbolic PDEs. So anything to do with, for example, weather forecasting, fluids, aerodynamics, anything like that. Okay, so just to recap from last week, we looked at the advection equation. Okay, this is quite simple, first order linear PDE. This is the simplest of all hyperbolic PDEs. In practice, this is not of much use really, to be honest. Okay, it doesn't model much. All it models is pure advection. The reason we study it is because any scheme or any sort of numerical method that doesn't work well on that equation is not going to work well on more complicated equations. So it's kind of used as a sort of benchmark. Also, it's useful in this sort of introduction to finite difference schemes for solving that sort of equation. This is also rare because if the initial conditions, so this is the value of t, so when t is 0 and we've got some spatial coordinates x, if this function is the initial condition, then the exact solution to this PDE is given by this. Okay, so rather than x, you've got x minus vt. V is velocity. Okay, so that v there, that denotes velocity. So this is useful. It has an exact solution. So, like I said, we can use it to benchmark any of our numerical methods. And what we do is, as usual, and you're starting to get used to, hopefully you're starting to get used to this process by now, you replace your derivatives with finite difference approximations to derive finite difference schemes. So FDS means finite difference scheme. So that's just your numerical method. And towards the end of last week, we looked at this idea. Not all finite difference schemes are stable for this advection equation. The idea of stability is a bit of a thorny problem, and that's what we're going to be looking at today. Okay, so this is sort of pictorially what the advection equation looks like. This red line is the initial condition. This could be anything. I've drawn it as like a sort of inverted triangle here. It could be any sort of profile. Just because it's a triangle here doesn't mean that's what it should be. It just means there is some change in this sort of quantity. Just so after time, so after a certain amount of time, so after t seconds, what we have is we have this triangle, which was here, has been moved along up here. So the distance moved is v times t. Velocity times time gives you distance. Okay, so that's if this was our initial conditions, that would be our exact solution using the advection equation. Okay, we looked at two schemes for solving that advection equation. One worked, first order upwind scheme, FOU. You remember that from last week? That one worked. We looked at another scheme, which was the forward time central space, FTCS. That didn't work, and that's where we left it from last week. Work is because the forward time central space scheme is not stable. And that comes into what we call as Lax's equivalence theorem. Okay, this theorem states a scheme to be convergent, it must be consistent and stable. Convergent means over time, our approximated solution should sort of pretty much converge to the exact solution, given enough time and given enough spatial steps and points. Okay, so we want our schemes to be convergent, because if they're not convergent, they're useless. Okay, so that's something we want. So we have to have two things. We have to have a consistent scheme and a stable scheme. Last week, we saw that a consistent scheme, a scheme is consistent if it approximates a PDE you're trying to solve. Okay, that might seem a little bit sort of obvious. Okay, what's the point in using a finite difference scheme if it's not solving what we want it to solve? It can happen. Okay, sometimes finite difference schemes and numerical schemes get complicated, and you're working on them, and the output you get is nothing what you expect. You're like, oh, what's happening here? It might be because your scheme is not consistent. Okay, to test whether your scheme is consistent, all you do is you replace your finite difference terms or your finite difference nodes with Taylor series expansions, rearrange, simplify, and you should get back to the equation you're trying to solve. And we saw that last week with the first order upwind scheme. Okay, just replace it with Taylor series, do some simplification, and you should get back, in our case, it was back to the advection equation plus some error terms. If you get something which shouldn't be there, it means your finite difference scheme is not solving the equation you thought it was solving, and you've gone wrong somewhere. So consistency is fairly easy to show. And what we have is, after you've done all this, down to the original equation, you have this error term. So for example, for hyperbolic equations, you'll have an error for the time, and you'll have an error for the space, or an order. So the superscripts after the delta t and delta x, that's the order of your error. And that's what we call the formal accuracy. Okay, so in this case, we'd have a scheme. If this was our error for our given scheme, we'd have a pth order error in time and a qth order in space. Okay, the idea of stability. Okay, so consistency, we just check that it's solving the equation we want it to solve. The other thing is stability. Now, there are a couple of things we have to check for stability. The first one is a CFL condition. CFL stands for Courant, Friedrichs, and Louis. Okay, three mathematicians who came up with it. And for a scheme to be stable, it must satisfy a CFL condition, which essentially is this. Okay, so the absolute value of your velocity times delta, multiplied by delta t divided by delta x, it's got to be less than or equal to 1. So on the top, we have velocity times time. That's the distance. So that is the distance that your concentration or your whatever you're modeling is traveled over one time step, and divide that distance by your spatial step. That's your distance between your finite difference nodes. If that's greater than 1, we've got a problem. Okay, because you've got no way of knowing whereabouts it is. So this has to be less than 1. And what we often write is v times dt over dx. We often use c to denote that quantity. And c is known as a Courant number. Now, in this case, let's say we have a finite difference scheme that satisfies this. So let's say we have this is less than 1. C could be anything. It could be anything between 0 and 1. We don't want it to be 0, because if it is 0, that means your delta t would be 0, and we can't march forward in time. Okay, we're like frozen in time. We can't actually go forward. So it has to be greater than 0. But it could be any value between 0 and 1. Or can it? Okay, so let's say your scheme satisfies the CFL condition. That does not mean your scheme is stable. Okay, it has to satisfy the CFL condition, but just because it does, doesn't mean it is stable. So it's what we call a necessary condition, not an absolute one. Okay, so what we tend to do in practice is C is set to a number that ensures the finite difference scheme is stable. So if you know what your value of C is, you can calculate what your time step should be. Okay, so C times delta x over the velocity, which is just this rearranged, that gives you your time step. This is what we do in practice. So in practice, we don't know what our time step is going to be. We know what delta x is, we know what v is, and we choose a value for C. That information allows us to calculate what our time step can be. We want this time step to be as large as possible, but too large, and we violate the CFL condition, and it becomes unstable. So this is like a sort of a speed limit, the value of delta t. Okay, so that's what we tend to do in practice. Okay, so you know what your spatial step delta x is, you know what your velocity is, you know what c is, or you choose c, and you calculate what your delta t should be. The question is, how do we determine what our current number is? Okay, like I said, it has to be less than 1, but let's say our current number was 1/10. Okay, 1/10 times delta x over v, that will give us a small value of t, delta t. But if I chose 9/10, I'd have 9 times that value. The larger the value of delta t, the better, because we're doing less work. We get to the solution quicker. But we can't have it too large, else it becomes unstable. So that's what we're going to be looking at today. The idea of stability. And this starts at the bottom of page 65 in the notes. A little bit of a caveat before I explain all this. This is quite involved. I've actually sort of just scraped the surface of von Neumann stability analysis here. There are a lot of things in this which I'm not going to explain. If you do, what's the unit? Digital sound and image thing. Can't remember what the name of the unit is. If you do that and you're familiar with the Fourier series, you might want to read up more about this because it uses a lot of Fourier series. I'm just sort of going to cover just what you need to know to apply it. Okay, so I'm not going to go in depth. If you do want to go in depth, have a look at that footnote at the bottom of page 66. Basically, I've skipped over some and I've given you Hirsch is a very good book that explains it. But I'm just going to cover what you need to know for this unit. Okay, so stability analysis. You may have done this if you do ODEs as well. Okay, we're going to define an error, and I've called it epsilon. Now, this error is between the exact solution, big U, and your computed solution, little u. Okay, that's an error. Okay, and we're going to define G as a growth in error over 1 time step. So you got your values, you apply 1 time step, you apply a different scheme, and you've got a new set of values. Now, the change in error from this time step to this time step, okay, is going to grow by that G, the growth. Okay. And this implies that G is the error at the new time step divided the error at the previous time step. So what we want is we want this growth factor to be less than 1. Because if G is greater than 1, it means our errors are getting bigger and bigger and bigger as we go on, and it's unstable. So we need our growth to be less than 1. The error for the finite difference scheme will also satisfy your finite difference scheme. So here I've got the forward time central space scheme. Before I continue, you may notice I've used J in the subscripts rather than I. This is because in a minute we're going to be looking at imaginary numbers. And I don't want to confuse sort of the subscript I with the I imaginary number. So I've just used J here. So if you wonder where they come from, that's why. Okay, so this is a forward time central space scheme. Okay. Another slight alteration here is, remember, C is equal to V times delta T over delta X. So I can replace that with C, and I've got a simplified version. So that's my forward time central space scheme. We saw last week that it was unstable. Okay. Well, if that's the scheme, then the errors in the scheme is exactly the same. So the errors also follow the finite difference scheme. So if I know what the errors are at the previous step, I know what the errors are at the next step. When we use, and this is von Neumann stability analysis, when we use this, there are a couple of things which we take for granted or assume. The first one is your PDE is linear. Okay, we're working with the advection equation, so we've got a linear PDE. In practice, we also use this for nonlinear. Okay, mathematically speaking, a bit dodgy, but it seems to work, so why not? And we also assume it's got periodic solutions. Now, this assumption means we can use Fourier analysis. Okay. If you don't know what Fourier is, don't worry, you don't need to know. If you do know what it is, fine. Okay. So what we do is we substitute in these Fourier nodes. Okay, so remember J is one of your finite difference nodes. Superscript n is your what time level you're at. Okay, and we say the error is equal to the exponential of a times time. Okay. A is a number. Don't worry about it; it's going to disappear. So it's just at the moment it's just a number. Okay, so e to the a times time multiplied by e to the I, which is the square root of -1, multiplied by k, which is known as a wave number. Don't worry about that. That's going to go in a minute. Times x, which is your spatial step. Okay. Don't worry about a. Don't worry about a. That's going to disappear. Don't worry about k. That's going to disappear. I've left it in there so it's sort of more mathematically correct, but they'll disappear in the analysis. Okay. Well, this is for the J node at the time level n. If I go forward in time. So now time level n plus 1, what we have here is exactly the same, except instead of t, we got t plus delta t. So I've gone forward one time step. Here, we're on the time level n, the node to the right. So we've got j plus 1. Okay, so that's the neighbor to the right. Well, we've got this, except for instead of x, we've got x plus delta x. And similar for the node to the left. Okay. So what we're doing is we're going to take our finite difference scheme and we're going to replace all of the u's, all of these u's here. We're going to replace them with with Fourier nodes, with these. And so this is what we have. So I'm going to keep switching backwards and forwards here. So on the left we have UJN plus 1. So on the left, I replace it with this, equals UJ, which is that one, minus C over 2 times the node to the right, minus the node to the left. Okay. So what we can then do is we can do some simplification, and what we want to do is find an expression for G. Okay, what's that growth in error? Okay, so we just use the laws of indices, or laws of exponents, to simplify. So that's what we have. Okay, first thing we do, well, we can replace e to the a t plus delta t, because that will become e to the a t plus a delta t. So using the laws of exponents, we can do that. This one's exactly the same, I haven't changed it, and I've done similar here. So this would be e I k x plus I k delta x. Okay, so that's a step I don't normally do, but I'm just showing it for an example. Now what I can do is I can divide throughout by this, because we've got that there, EAT, EIK delta x, we've got it there, we've got it there, and we've got it there. So if I divide throughout, we start to see things simplify a bit. Okay, so we get down to that. This e to the at, that's your growth. That's the growth in error. Okay, I'll explain that now. Okay, so G was defined as being the error at the next time step minus the error at the current time step. Well, the error at the next time step is this. The error at the current time step is that. You divide it out, we just get e to the a delta t. And that's what we've got here. So this describes what happens to our error over one time step. And we don't want our error to grow. So we want e to the a delta t, we want that to be less than or equal to 1. Okay, so that's the amplification factor. That's what we want, less than or equal to 1. Okay, why do we want that less than or equal to 1? Because the errors do not grow. If the errors grow, after a few time steps, they're just going to dominate the solution. Okay, so we have this. A bit of a thorny problem here is we've got a couple of imaginary numbers. So there are various techniques which we can get rid of these. This one's quite nice because using this, have you seen this trig identity before? Anyone heard of Euler's identity? Okay, most beautiful equation in mathematics. Look up Euler's identity, it will blow your mind. You don't believe me, do you? No. Look at the Wikipedia article on Euler's identity. Anyway, from Euler's identity, we get this. So sine x is linked to the exponential function with the imaginary number in it. Okay, that's amazing. The fact we've got a trigonometric function is linked to the exponent of an imaginary number. I think it's beautiful. But anyway, you can look this up if you want. So sine x is equal to this. Well, if you notice in here, if you say k delta x is x, we've got e to the ix minus e to the minus ix. So that's what we've got on the top. Okay, we divided by 2 here. Okay, so if we put this into there, we get that. Okay, so we have 1 minus I c sine k delta x. Okay, and that's got to be less than or equal to 1. But if you notice, this is the magnitude. Okay, and if you've got a magnitude of a complex number, you simply square the real part, you square the imaginary part, and then you square root it. So, for example, the complex number is of the form a real part plus I times the imaginary part. The modulus of that is a real part squared plus your imaginary part squared, square root it. Okay. So all I have to do to calculate the modulus of this is to square 1, which gives me 1, to square I. Now, by the definition, I squared is minus 1. So multiply minus 1 by minus 1, you get plus. Square the c, you get c squared. Square the sine, you get sine squared. Square 1 on the other side, you just get 1. I've gotten rid of that nasty imaginary number. Okay. So for stability, I need this c to be a value that satisfies that inequality. Now, sine squared x is always greater than or equal to 1. I'm sorry, greater than or equal to 0. Because it's going to, whatever, it's a wavy line between 0 and 1. Okay? So if this is always between 0 and 1, c has to be positive. We can't have c being negative. So this is always going to be a positive number. C squared is always going to be a positive number. And I'm adding a positive number to 1. But I want it to be less than or equal to 1. So the only number for which c satisfies that is c is equal to 0. So it only holds for that value of c is equal to 0, which would imply that delta t is equal to 0. Because remember, c was equal to, what was it? It was v times delta t over delta x. So if c is equal to 0, delta t is equal to 0, but we can't go anywhere. Imagine getting into a car and the maximum speed in a car you can do is 0 miles an hour. You're not going to go anywhere. So this means the forward time central space scheme is unconditionally unstable. It can't be used. It's rubbish for this equation. It may be of use to a different type of equation, but it can't be used for this one. Okay, so I'm just going to summarize what I spoke about. Essentially, there's 3 steps to this stability analysis. You replace each of your u's with your Fourier node component, rearrange to get g, and then you've got to use this condition, okay, to try and determine a range of values for c for which the scheme is stable. That stage can be a bit tricky. Okay, often we have to use trigonometric identities, which I just showed with the sine function. or properties of vector norms. Okay. And if you find that there's no possible value of C that satisfies this, we have an unconditionally unstable scheme. It's useless. Can't use it, move on. Try something else. If we have certain values of C for which the growth is less than 1, we have a conditionally stable scheme, and that's most of them. Most finite difference schemes have some form of condition on that value of C. If we're really fortunate, we have a scheme where all values of C satisfy this, we have unconditionally stable. Okay, that's only the case if we use what's called implicit schemes. So those of you doing ODEs, Runge-Kutta methods are explicit, so they have a range of stability on them. Implicit Runge-Kutta schemes can be unconditionally stable. Okay, so what we're going to do now is just have another look at this example. And this is on page 68 and 69. This kind of this von Neumann stability analysis, it feels a bit weird when you first do it, but it's not that difficult. Okay, this is what we did last week. Okay, so I just talk over this again just to refresh your memory. So this works example show that the first order upwind scheme is consistent for the advection equation. So there's the scheme. Those are Taylor series. Substitute in the Taylor series, and eventually, if you simplify down, you get the advection equation plus some error. Okay, so this means the first order upwind scheme is consistent, and it has error of big O delta t and big O delta x. Okay, over the page, we're going to be looking at von Neumann stability analysis. I'm just going to write out the scheme again. Okay. Oops. Write out the scheme again. I might as well get it right. Okay, notice I'm using J's just to avoid confusion with the imaginary number I. If you remember, it's minus v dt, so minus v delta t over delta x. Actually, I'll write it out. I'll show you what I'm doing. So we've got v dt over dx, and it's the upwind scheme, so it's using the nodes to the left. By the way, if you notice the way I write my v's, I use this little tick afterwards. That's because my v's look a lot like my u's. So if you're wondering why that is, it's just because if I was to write v like that, because I'm a bit sort of careless, my v's start to look like u's. So I put a little sort of horizontal tick after it just to make it look like a v.
Now they look like your arse.
Can't win, can I? That's a v, all right? My R's look like that. I don't have that little thing. My Z's are like that, so I don't think these are the 2's. Anyway, I digress. Right, so what I'm going to do is C is equal to v dt over dx. Okay, so I can rewrite that in a little bit simpler terms, like that. That's a C, by the way. Okay, I'm going to do a little trick in a minute because I've done this quite a few times before. This trick makes things a lot easier. You can do this in one of two ways. Without this little trick, you go on to use trigonometric identities. I don't like them, they're complicated. But I'm going to rewrite this. Okay, if you notice, we got UJN there, and we got minus C UJN there. So I'm going to factorize those out. What I mean by that is I've got 1 lot of UJN jn there, and I've got minus c lots of u jn there. By the way, that's a bracket. Okay, and I've also got minus c times minus uj minus 1 there. So that's plus c uj minus 1x. Okay, so that's my scheme. I haven't done anything to it. It's the same scheme. I've just rewritten it in a particular form. Okay, the next step is to insert our Fourier nodes. So what I'm going to do is substitute. I just spell substitute. T-U-T-E, right? Okay, so that's what I'm going to substitute in. Okay, so on the left-hand side, I've got E, but it's the n plus 1, so I'm going to say A t plus delta t, and E I k x. Okay, because it was the n plus 1, okay, I have t plus delta t in place of t. And that's equal to the 1 minus c. I've got ujm, which is just this one here. Okay, and then I've got plus c uj minus 1, so I'm going to have x minus delta x. Forgotten the I and the K. Okay. Obviously, multiplication is commutative, so it doesn't matter what order you put them in. Okay, so that's substituting our Fourier nodes into our finite difference scheme. So we're assuming that our errors follow the finite difference scheme, which they do. So if our errors can be described by these Fourier nodes, we substitute them in. And I'm going to do a bit of simplification. First thing we're going to do is we can use the laws of exponent and just expand these out. So I've got EAT, so E to the AT, multiplied by E to delta T. Okay, multiplied by E to the IKX. 1 minus C, E to the AT is all the same. So I'll move my hand in a minute. E to the IKX, E to the minus IK delta X. Okay. Straightforward laws of exponents, nothing special about that. Okay, all of my terms in that equation have a term in common. It has that e to the AT, e to the IKX. So all the terms have that, so I can get rid of that by dividing throughout. So we have e to the A delta t. Okay, so that just gets rid of those two. That one just disappears to 1. Okay. Those two disappear, so I'm left with e to the minus I k delta x. Okay, let's start to look a lot simpler now. That e to the A delta t, that's my growth. So because G is equal to E delta t, for stability, we want G to be less than or equal to 1. So I'm going to replace that with 1. I'm going to replace that with like a greater than or equal sign. So therefore, notice I've got these aren't ones, they're modulus signs. Actually, I should really rewrite my ones to be a bit more like a one then. Okay, we've got a problem. We have that pesky I there, imaginary numbers floating around. We're going to call on Euler's identity again. They tell you it's beautiful, didn't they? Yeah. Part of your homework for me is look at Euler's identity. Last year's students took the piss of it. At the end, they bought me a T-shirt with it on, with my name underneath saying the most beautiful equation. Taking the mickey a bit there, I thought, but fair enough. Anyway, yeah, so we got that pesky I. That's hanging around, we don't want that. But we have a modulus. Okay, we need that modulus to be less than or equal to 1. We're going to use triangle inequality. So the triangle inequality is A plus B is less than or equal. Oops, it's not a vector. That's what the triangle inequality is. The whole is less than the sum of its parts. Ever heard of Gestalt theory? Sort of philosophy. The whole is greater than the sum of its parts. If you take a football team, you take all the separate players on their own, and if they're not working together, they'd be rubbish. If they work together, they're a lot better, they can achieve more. That's Gestalt theory. This is sort of anti-Gestalt theory. Okay. So this is triangle inequality. So what that means is I can split up this. Okay, so I've got the 1 is greater than or equal to 1 minus c. There's a 1 there. Okay, so instead of having, imagine that's A here, and that's B there, I can have the modulus of that plus the modulus of this. So it's minus I, K, down to X. Okay, still got that imaginary number, don't worry, it's going to disappear in a minute. Well, one feature of moduluses, or moduli, is we can also split them up. So C times E to something, or the modulus of C times E to something, is the same as the modulus of C times the modulus of E to something. So we got down to this. Now this is what I wanted. I wanted the modulus of a negative exponential. The reason why I wanted that is because by Euler's identity, the modulus of E to the I times anything is 1. Another thing from Euler's identity. So this is just going to be 1. Okay, so what do we have? We have 1 minus c plus c. Okay. And we're looking for this right-hand side to be less than or equal to 1. So for what values of c is that satisfied for? Well, let's take c is equal to 0. So you've got 1 minus 0 plus 0. So that's okay when c is 0. What about when c is 1? So we've got 1 minus 1, which is 0, plus 1. That's fine. What about when c is 2? So here we've got 1 minus 2, so that'll be minus 1. But the modulus of minus 1 is plus 1. Plus 2 would be 3. So c can't possibly be 2. In fact, c can only be in the range 0 to 1, because this first one here has to be between minus 1 and 1. Because if it's outside that range, if it's minus 2, it will violate this condition. So what that means is c has to be less than or equal to 1 for stability. Okay, so this implies our delta t, okay, it's going to be less than or equal to delta x over our velocity. That's our limit to our time step. It can't be more than that for the first order upwind scheme. So we take our spatial step, divide it by the velocity, that's our upper bound for time. If we go above that, it becomes unstable, and it just crashes and the whole world falls apart. If it's below that, we're all fine. Maybe a bit melodramatic with the world falling apart a bit. But okay, so just to sort of recap on that, I know it looks a bit strange, but it's not too bad when you've had a bit of practice. All I did here was rearrange it to a nice, simpler form, substitute in the Fourier nodes, and you get down to this. That's kind of the easy part. What we've got to do is got to somehow find a way to determine what the value of C is. Okay, this can be a bit tricky. This is fairly simple. Okay, but how you determine C is up to you. Use whatever tools are available. Right, so I'm just gonna. Is that okay for me to change the? What I'm going to do now is actually just switch over to MATLAB. Okay, and here's one I did earlier. Maybe not. Oh, I've broken it. Hello? Oh no. I've broken MATLAB. Oh, no, there's one there. What's it doing? Okay, I'll come back to that. Okay, so I'll come back to that. Okay, so far we're trying to solve this one-D advection equation. We've got the first order Atwood scheme, which we just showed is stable and it's consistent. We've got the forward time central space scheme, which is consistent, but it's not stable. So we can't use it. What I'm going to do now is go on to look at other examples of finite difference schemes. And the first one we're going to look at is called Lax-Friedrichs. And essentially what Lax and Friedrichs tried to do was take the forward time central space scheme and make it stable. Okay, they liked the fact that it was second order in space, but didn't like the fact they couldn't use it because it's not stable. Okay, so what Lax and Friedrichs did was, again, we take a forward difference in time, central difference in space, but with the forward difference in time, we average, instead of UI, okay, we take in the node to the left, node to the right, add them together, divide by 2, and so your central node is the average of those two. If you do this, it becomes stable. Forward time central space scheme becomes stable. Rearrange, bit of algebra, and we get this. Okay, if you look at the order of the error, okay, it's delta t and delta x. But hang on, we've used a central difference in the x derivative, that's second order. This should be second order. But because we did this sort of averaging here, it sort of negates that second orderness. So it's still only first order. Okay, there's a stencil. So we're trying to calculate this node. And so what we do is we don't actually use this node. We use 2 nodes either side. So take these nodes, add them together, divide by 2. Take the nodes, subtract the right node from the left, multiply by v dt over dx, and divide that by 2. Okay, and that's your Lax-Friedrichs scheme. If you do a binomial stability analysis, which is part of your exercise for the lab sheet 4, you can see it's stable when C is less than 1. And there's a solution. Okay, so the red, I was open to try and actually find, is that MATLAB woken up yet? No, broken MATLAB. Broken the whole computer as well. Nope, not having any of it. Okay. The red line is the analytical solution. What the red bumper's done is it's gone out here. I've used periodic boundary conditions, so it then appears back in that way and then finishes off where it started. The blue dots are the computed solution. Okay, and that's for Lax-Friedrichs. And you can see we have this dissipation here. Okay, that's sort of an error. Okay, it should be up here, or the blue dot should be up here, but we've got this error. That's a feature of first order schemes. First order in space means we have this dissipation. It's not good, so we can't really use that one. Let's have a look at a different technique. Next one's called the leapfrog, for obvious reasons in a minute. I'll show you why that is. Now, the leapfrog scheme says, right, what we're going to do for the partial derivative in terms of t, we're going to use a central scheme. So we go forward a time step and backwards a time step. Divide that by 2 delta t. And also use a central scheme, central difference approximation for the x derivative. Okay, rearrange that all. So we want this to be the subject, and this is what we get. In this case, notice we have the node for ui at the previous value, and these are at the current. Okay, so what that means is this node is what we're calculating. What we do is we take that node, which is 2 time steps back, okay, and minus v dt over dx times the difference between those. So it kind of leapfrogs that point. So to calculate that one, it goes 2 time steps back to that point and sort of leapfrogs. That's why it's called a leapfrog scheme. Okay, the only problem is we've got here is, what do we start with? Let's say this is our initial time level here. This is our, let's say when n is 0. We don't have a previous value, it didn't exist. So in that case, we borrow the forward time central space scheme. So this is forward time central space. But I've just gone to great lengths to show you that it's unstable. But it doesn't matter because we're only using it once. Any errors in it haven't had time to accumulate and become unstable. So we use that once to like a starter. Think of your start motor on a car. Okay, just to get it going. And then for all other time steps, we use this leapfrog. Okay, and that's the solution. So that's pretty damn close. Okay, so there's your red line just underneath it, your blue dots. It's not absolutely bang on. It never will be because we're always only approximated, but it's pretty damn close. So that may look pretty good. In a minute, I'll show you why it's not as useful as you might think. Okay, Lax-Wendroth. Okay, by the way, I'm not expecting you to remember all these names. You know, if it comes up in an exam or in a coursework, I'll sort of let you know what each one is. So you're not expected to sort of reel these off by heart. Now, the Lax-Wendroth is what we call a 2-stage process. It's a predictor. You calculate like a half step, and then you correct that half step to calculate the full step. So sometimes called a predictor corrector. And what we do is we're trying to calculate this one here, and for a half step, we're going to take this sort of halfway point. It's like a staggered, what we call a staggered grid. So I've gone halfway up your time step and halfway along the spatial step. Okay. And I'm going to calculate that using Lax-Friedrichs. Okay, so this node here is calculated using Lax-Friedrichs based upon these two. And then I do the same for this node. So again, we've gone half a time step forward and half a spatial step back. Again, I calculate this using Lax-Friedrichs on those two. Then what I can do is I can use a leapfrog to go from there to there. So a leapfrog over one time step, leapfrogging over this sort of half level. Okay, so that's, we calculate those two from Lax-Friedrichs, then use a leapfrog to jump over. Okay, and that's sort of the leapfrog scheme. In practice, we don't use 2 steps. We can combine it into one. So the blue and the red there are my Lax-Friedrichs solutions. So there's a Lax-Friedrichs for that one. Okay. And there's a Lax-Friedrichs for the red one. So you can do a bit of algebra, simplify, and you get this. Okay, notice that looks fairly similar to the second order finite difference approximation of a second order derivative. Okay. And this is the stencil, so all I need is 3 nodes at the nth time level to calculate that node there. Okay, and similar to the leapfrog scheme, gives us a very nice solution. So we don't have any of that dissipation which you saw with the first order schemes. Okay, we've got one more. Yeah, Frank-Nicholson. All of the previous schemes are what we call explicit. It's dead easy to calculate them. They're just explicit relationship. The Crank-Nicholson scheme is an example of an implicit scheme. Okay, and what it does is it uses a combination of 2 separate schemes. One is a forward time central space, which we've already covered. The other is a backward time central space, which is very, very similar. So here's a forward time. So we've got step forward in time minus the current time level. Okay. This one's backwards. Oh yeah, you can see here. Okay, this is based upon new sort of time steps. And what Crank and Nicholson did was they averaged it. Okay, so you add them together and divide by 2, and you get this. Now this is an implicit relationship, because what it says is, I want to find the value of a node at the n+1 time step, because that depends upon the values of the node at the n+1 time step. So if I calculate this, that's going to have a number, but that's going to change that number. And if that number changes, that number changes. So we have like a circular relationship, an implicit relationship. Okay, so there's the stencil. So if I want to calculate the value of that node, I need the value of all of these. Okay, but let's say I calculate that one and then move over to the next node. That node is going to depend upon the value of that node. Well, that node depends upon the value of that node. So it's what we call implicit. These tend to be a bit more involved to actually calculate. Good thing about the Crank-Nicholson scheme is it's unconditionally stable. That means we can pick whatever value of delta t we want. We don't have to worry about stability. But if you pick too large a value of delta t, you're going to be your accuracy won't be as good. Okay, I'm not going to ask you to apply the Crank-Nicholson scheme. It's a bit too involved, but I will sort of go through the basics. So there's our scheme, and just for ease of use, I'm going to let R is equal to V times dt over 4dx, just so it sort of, this is going to be a constant. Okay, and what I've done is I've put all the n+1 values onto the left-hand side. Okay, so that value there and that value I've put over to this side. Okay, and on the right-hand side, I've just left with the current values. You know what these are. We know what the values of those are. We don't know what the values of those are. The other ones are. So this is a linear system. So for whatever value of I, whatever your node is, you've got, let's say you've got 10 nodes, you'll have 10, took a while to come up, didn't it? You'll have 10 linear equations. Go away. What was I? Spinning beach ball of death. Oh. Well, I'm just going to sort of drag that sort of down there, yeah. Oh no, somebody's gone a bit pear-shaped. Where was I? Yeah, so say you have 10 finite difference nodes, you'll have 10 equations like that. Linear equations, you can solve them using Gaussian elimination. For the left and right hand boundaries, okay, you'll end up with these values here, that one and that one there. You know what they are, you know the values of them. If we're using periodic, like we are in this example, u minus 1 will just be equal to un minus 1. Okay, and that one there will just be equal to u1. Okay, so if you write it as a matrix equation, I mentioned it was linear. Okay, so in the form of, if you're familiar with A times X equals B, these are all known. That's just a vector of known values. Those are all known. That's just a matrix, coefficient matrix, and you can solve that using whatever method. Preferred method is probably SOR method. And that's the solution. So after all that effort, put quite a bit of effort into using Crank-Nicholson. It's not actually very good. You can see we've got a little wobble here, a little oscillation, and we're sort of lagging behind the solution up there. Crank-Nicholson is very good for when you've got problems, stiff problems. Stiff problems tend to have quite stringent stability constraints. Right, so those are various different solution techniques. Okay, that problem I just showed, that one with the Gaussian curve, that's quite an easy problem to solve. The reason it's easy is because the change in gradient is gradual. If I sort of look at the change in gradient, there's no sort of abrupt change. Okay, so another test is what we call the top hat test. So here we've got a top hat function, so it looks like a top hat, and it has these very, very abrupt changes, these sort of abrupt changes in direction. And this is quite difficult for a scheme to actually resolve. So this is the first order upwind scheme, and you can see we've got a bit of an error here. It's nowhere near the corner, and we've got smoothing down here. Okay, the Latch-Friedrichs is even worse. Okay, you'll notice the Latch-Friedrichs, each sort of node tends to pair up with a buddy. You can see you've got this sort of jagged sort of profile here. So that's no good because, again, it hasn't resolved that corner. Okay, next one was leapfrog. Bloody rubbish. Okay, all over the shop. Okay, so this is all over the shop because of these abrupt changes in gradient that caused it to go a bit doolally. So we can't use leapfrog to solve this. Okay, next one, Wendroff, that's the best one. Okay, so with the Latch Wendroff, you can see we've got a little bit of smoothing, but it's better. We do have this overshoot. Anybody do signal processing here? Yeah, what's that called? Starts with G. Gibbs phenomenon. Okay, so we've got a little bit of an overshoot. Okay, that is a feature of second order solution methods, and we've got an undershoot down here. That's the best of the bunch. It's a hard test, this one. Crank-Nicholson, again, similar to the leapfrog, all over the shop. At all. Okay, so that is solving the advection equation and stability. The reason why we solve the advection equation is because if I was to use any of these schemes, if I go back through them and it's going a bit slow. No, it's not playing. If I was to use any, let's say I was to use a Crank-Nicholson scheme on a tougher, more complicated hyperbolic equation, it'll be all over the shop. Ooh, that's going to be beautiful. It'll be all over the shop. So there's no point using that. The best one is Latch Wendroff, even though it's got that little overshoot. Okay. Right, any questions? Again, you look like bunnies in the headlights. Is that sort of, have I totally lost you, or is it okay? Sorry? Different equations. So non-hyperbolic equations. So, for example, parabolic equations, they'd be better. That was a good question. Question just said, so these schemes are rubbish, the advection equation, so when do you use them? Good for parabolic equations. Okay, the forward time central space scheme is actually very good for a parabolic equation because it happens to be stable. It's not stable for the advection equation. Essentially, you just try it out. So there's no sort of magic rule. You just try it. Is it working? No. Try something else. Okay. Don't forget. The lab sheet 3 should be finished by Friday. That's the one with solving the Laplace equation. Later on today, the project meeting, project talk. Jan's doing a talk on LaTeX, and there's a workshop tomorrow if you be free at 1 o'clock. Hop along with any work you've got, any later work, we'll give you a hand. Okay, so see you next time.